Hello, learners. Welcome to the topic on Nano in Nature. I'm Dr. N. Sudha, working as an assistant professor in Department of Physics, Sri Shada College for Women, Salem. Let's enter the nano world. First, let us see the scale of things. The left side of the scale, you can see the natural living things from the cat, the butterfly, bee, fly ash, red blood cells, and finally the DNA at 2 nanometer wide. While the right side of the scale shows the man-made fashion articles from the pot, the head of a pin, microelectronics, and finally at the nano world, quantum quarrel atoms. Here you can see a timeline of industrial revolution which took decades. In fact, the industrial revolution was overall more good because it shaped life and made society better. But the revolution we are currently facing is revolution in nanotechnology, and it took only few years for this. The variety of applications for nanotechnology has given this discipline a great potential to transform the economies of countries and change the production process of their industries. Thanks to Richard Feynman, who found that there's plenty of room at the bottom. Yes, nature is out there, standing as a giant laboratory of science and engineering. For centuries now, we have been trying to understand nature's strategies and apply what we learn from them to solve our modern problems. Nature's nanotechnology and biomimicry is making our dreams a reality. Nature has given solutions to these daily problems. It's really fascinating to realize that scientists are inspired by nature's facts. Let's explore the science behind nature and how imitating them has helped us to develop many technologies. Let me now define what is nanobiomimicry. Biomimicry is simply examining nature or its processes and taking inspiration from that to solve human problems. If it has worked in nature for thousands of years, why don't we give it a try? By natural nanomaterial, here we mean materials belonging to natural world, the animals, plants without human modification or processing, and that have remarkable properties because of their inherent nanostructure. Here we can see some pictures of spider's web, 10 images of some viruses, and naturally occurring photonic crystals due to nanoscale structure. Such natural inorganic crystals occur through crystal growth in diverse chemical conditions of Earth's crust or due to volcanic activity. Nature is actually full of nanoscopic architectures. Let me now cite some of the examples where we use it in our everyday life. Shark skin. Sharks have been swimming in the oceans for millions of years without the problematic accumulation of algae or fungi on the surface of their skin. Can you guess why? This is because the nanoscale patterns on the shark skin can deflect the accumulation of brancles, algae, and bacteria, which is called as anti-fouling. The surface of the shark skin has self-cleaning, anti-biofouling, hydrophobic, drag-reducing, and aerodynamic characteristics. The anti-biofouling and self-cleaning properties of the shark is attributed to nanostructured riblets found on the denticles, which you can see over here. The size and shape of these denticles vary between shark species. The microstructure of the skin also facilitates high-speed swimming up to 90 km per hour, allowing sharks to hunt their prey. The presence of these microstructures distinguish sharks from their aquatic species such as whales, which are covered by brancals. This technology has been applied to the surfaces such as for maintaining functional pipelines, underwater ships, submarines, submerged infrastructure technologies. Gecko's adhesive system. Geckos have the unique ability to scale vertical surfaces with both strong attachment of their toes to the surface coupled with easy and rapid removal. They are able to do this due to the attractive forces of the millions of nanoscale hairs present on their toes known as setae and spatula. These create a frictional adhesive to other surfaces by increasing the surface area of the toe, meaning more of the toe actually interacts with any given surface. The attractive forces that play here are called as van der Waals forces. These are weakly attractive forces that exist between nearly all chemicals and materials. Geckos turn these weakly attractive forces to adhesive attraction. Gecko have 500,000 hairs per toe, hundreds of projections per hair. So that means it could lift a child weighing 45 pounds. The various applications of the gecko's adhesive system are given in robotics, gecko's adhesive, fumble-free football, vehicle tires, training shoes, and rock climbing aids. Gecko's tape. Gecko's tape provides potential for a new adhesive that can cling onto any surface yet can be removed without any residue. Additionally, Gecko tape has an attractive force proportional to the amount of weight it carries, allowing for more stability in adhesive loads. While Gecko foot has a made up of keratin to make up Gecko tape, Jim and colleagues prepared flexible fibers of polyamide on the surface. You can see it can bear a weight of a human being. Wow, very interesting, isn't it? Blur to Velcro. Velcro is the brainchild of Georges de Mastral, a Swiss engineer, who in 1941 went for a walk in the woods and wondered if the burrs that cling to his pants and his pet dogs could be turned into something useful, that is, the Velcro tape. The Velcro Nano tape is reusable. Its features are its sturdy nano material. It's not only easy to break but can be reused. Easy to disassemble it. It can hold items weighing up to 1 kilogram on a smooth surface. When the tape loses its viscosity, it can be rinsed with water. Do not use it on rough surfaces, dusty walls, greasy and damp surfaces. This is suitable for any occasion such as pasting photos, posters, fixing carpet pads and pasting items on the walls. All of us like the lotus flower. Now let us see the lotus effect. The super hydrophobic power of self-cleaning. The leaves of lotus flower exhibit extremely water repellent properties due to the micro and nanostructures on the leaf. These structures allow the plant to have a magnificent self-cleaning function. This concept has been extrapolated in various applications like windshields, waterproofing phones, protecting fabric in woods and other surfaces from dirt, dust or car exhaust particle residue. Butterfly wings. Butterfly wings have layers of nanoparticles separated by layers of air. The thickness of the layers changes the colors that we see. The nanostructures are coated with hydrophobic wax crystals approximately 1 nanometer in diameter. This makes the surface at the nanoscale quite rough. Butterfly colors, besides repelling water and color, the nanoscale make butterfly wings self-cleaning. That is, it removes the water and the dirt. These nanostructures don't just make them pretty, but also makes them clean by shedding water and dirt. This changing color of butterflies is due to interference within the structure. By mimicking the microscopic structure in the wings of the butterfly, an international research team has developed a device smaller than the width of hair that could make optical communication faster and more secure. Toucan beaks. This is also an interesting nano in nature. The exterior of the toucan beak is made up of overlapping nano-sized tiles of keratin, the same protein that makes up our hair, fingernails, and horn. The interior of the beak is a rigid foam made of a network of nano-sized bony fibers connected by membranes. This allows the beak to absorb high-energy impacts. The nanostructure of the toucan beaks has inspired automobile companies that have made automobile panels that could protect passengers in crashes and also inspired construction of ultra-light aircraft components. Mother Nature can sometimes be peculiarly amazing. She hides some of her greatest of creations in simplest of creatures. For 450 millions, spiders have made web. Spider silk is a smooth fiber which is completely made up of proteins. The web protein based nanomaterials that is self-assembled into fiber and sheets. Secret to this strength is in the special nanoscale arrangement of these protein molecules and the nanostructures they make inside the silk fiber. Another amazing property of spider silk is its ability to stretch while maintaining a high tensile modulus. Many other conventional high modulus materials like steel or armored fibers have comparatively low breaking strain, which make it less tough. However, spider silk is tougher than both and takes more energy to break. Here you can see the graphene which has been mimicked from the spider's web. The potential application of the spider's web is tremendous. The characteristics of this polymer nanofiber has given application in aerospace, automotive systems, civil and structural engineering, medical devices, and robotics. Dear learners, nanoscience is one of the technologies of the 20th century which has potential to offer sustainable solutions to many of our scientific problems through the key of nanobiomimicry. We have seen only a few examples, but there are many more. Nanobiomimicry has taken lessons from nature, giving extraordinary results, proving that nature is a best teacher. Thank you for watching and wish you all a very happy learning.